That what you have studied? Element, basic element, circuit element, what you have studied? In between insulator and both the side conductor. What is that material? I mean device.
Capacitor with dielectric.
Capacitor. Yes, you are correct. See, this kind of element is nothing but capacitor. The positive terminal of the battery is connected to the top material and negative terminal connected to the bottom material. Okay, these materials may be conductor, fully conductor or semiconductor, doesn't matter, but it is a capacitor because you have in between things that is insulator. This is an insulator. This insulator may be silicon dioxide in a specific case or any other insulator. Mica in your case of capacitor. Okay, so we are trying to say it is a silicon dioxide, one kind of insulator. Top material may be conductor or semiconducting material like polysilicon. At the bottom may be conductor or semiconducting material like doped silicon, p-type doped silicon. Suppose if it is semiconductor, then p-type lightly doped silicon. P-type silicon, which is also called, say, substrate. In this case, we are considering this thing. Anyway, so once you apply positive voltage at the top terminal, and hence what will happen? Corresponding to each positive charge deposited at the top terminal or top material, there will be negative charges at the bottom terminal. That happens in capacitor. I hope you are aware of this. Aman?
Yes, sir.
So now, if you increase the, say, V1, I am calling it, increase the voltage, what will happen? Because you know, we're talking about capacitor. So capacitor is what? Sorry, let me write in this way. Q, charge across the capacitor. Q is equal to C V1 or not? Let me call not VI, it is, I'll be calling it V1. V1. So if we increase the V1 and C remaining constant, what will happen? Charge will increase? Yes or no?
Yes, sir.
If since this relation, let me call it, if V1 is increased, okay, then what will happen? What will happen to Q? Q will increase. So more charge will be there if I increase the voltage. So correspondingly, here more negative charges will be there. Actually, charge, I mean electrical flux or field line will be originated from negative charge, a positive charge, and terminate at negative charge. So every positive charge should have a negative charge at the bottom plate. Are you getting my point? From the positive charge, electrical flux or field line will emanate, and it will end at the negative charge. So in this way, corresponding to all positive charge at the top, there will be negative charges. So once you have increased the V1, Q will increase if C is constant. Do you agree or not? C, capacitance of this, and C is what? epsilon 0 epsilon r a by d. Okay, so this d is what? This distance d, let me call it thickness t, or it is oxide, silicon dioxide, so I am calling TOX, oxide thickness. Okay, so here instead of d I am writing TOX. So if d or TOX, second point I am writing here, if d or TOX here is decreased, what happens? What happens to C? Tell. C increases or not?
Increases.
C increases, and then hence what happened to Q? Q. Suppose Q V you are keeping constant and decreasing the oxide thickness. What will happen to Q?
Increase.
Q will increase. I mean, these are the things you can manipulate and have different values. Okay, V1 increase, Q increase. If C is constant, if V1 is constant and QX oxide thickness decreases, C increases, so Q increases. Now, in this case, suppose, let me delete some certain portion I want to have and clear it. Suppose now I want to here make a contact point. Okay, this contact point I'm making here, another contact point I'm making here. This contact point, from this contact point I am connecting a supply voltage. Okay, mm-hmm. Mm. Mm-hmm. Good morning. Another supply voltage V2 I'm connecting. What will happen now? The negative terminal of the battery is connected to, say, point B this side, and this side I'm calling A. Right? And what will happen? These electrons, this side, left side, the negative terminal will be pushing the electrons towards terminal A. So electrons will move in this direction. Okay. And conventional current will be in this direction. So current from A to B, electrons from B to A. Do you agree or not? Yes or no?
Yes, sir.
Yes, sir.
So suppose you don't have B1, then there is no electrons, current will be there. because this we have taken as, the bottom plate I have taken as p-type silicon, p-type silicon, okay, or let me say substrate. So p-type means few holes will be there, lightly doped I am telling. So this hole will be there all around. There is no electrons. Okay. So if there is no positive voltage V1 applied at the top terminal with respect to the bottom terminal, there is no positive charge at the top, so there is no corresponding negative charge. So current will flow or not from drain to, I mean, A to B. There is no free electrons. But yes, if you apply positive charge at the top terminal, bottom terminal have holes. But yesterday in the last class we discussed that in a p-type materials also, due to thermal generation of electron hole pair, there will be certain number of electrons, and those electrons can be attracted if your V1 is strong enough to do so. V1, if small, initially repel the holes, creating a depletion layer, negative ions. Okay, negative ions will be there at this region. Because the holes are repelled, negative ions, depletion layer will be there. Did I say yesterday? If your material is p-type, holes are there, but at the top you have applied a positive charges. So those positive field will repel the holes, leaving behind a depletion layer having negative ions. Okay. Now further, if you increase the V1, I mean more number of positive charge at the top material, then what happens? Correspondingly, its electrical field will increase. It will apply more pull. Okay. Okay. So that pull will, I mean, attract the myotic carriers in this p-type substrate. Myotic carriers are electrons. Those will be collected and lined up here at the bottom portion of the silicon dioxide insulator. So instead, in the absence of this B1, there is no electrons in this region, top portion of the bottom layer. So there is no current from A to B. Do you agree or not?
Yes, sir.
So if I should write that if, now point number C I'm writing, if V2 is connected, V2 is connected between A and B, current electron from B to A, and hence conventional current from A to B will flow. This is understood or not?
Sir, understood.
If V1 increases, electron density will increase or not? If, as we have V1 increases, then the charge density or electron density, let me say, because if V1 increases, the electron density, electron density means between A and B, I am showing some electrons, number of electrons. Are you getting that?
Yes, sir.
That electron, if V1 increases, then the electron density will increase, because positive charge density at the top plate will be increasing. Okay, because of that, more field, more attraction, more electrons. So current will also increase. Current will increase, obviously. Electron density increase, current will also increase. So what it is meaning? It is meaning that if we increase the voltage V1, your current increases. You get voltage current control correction. It means we get a voltage controlled current source. Current source means something like this. Suppose if I denote it like this and apply voltage, okay, this is your V1. If you increase V1, you get more current in this direction from A to B. Or in other words, I can show the characteristic like this. This is, say, current I am denoting as IAB. IAB initially will be negligible or very small or negligible. But if V1 increases to a certain value, then current will increase as it is shown here. It's going to act as a voltage controlled current source. Okay. See, initially, this is, say, voltage here, V1 is around, say, 0.1 volt or 0.2 volt, 0.3 volt, such a small value. Such a small value. In this, suppose you have applied 0.3 volt or 0.4 volt, whatever you want to. Between A and B, these two terminal, you have applied 0.3, 0.4, whatever is, smaller voltage or 1 volt, whatever is. If you apply even 1 volt across AB, current will not flow if your V1 is 0, because there is no free electrons there, which will carry the current. But if you apply sufficient amount of V1, initially 0.1 volt, 0.2 volt, 0.3 volt amount of very small amount of voltage will repel the holes down, creating a deflection layer. Okay. But if you increase further V1, then stronger electrical field will attract the minority carriers in the P-type material, which is at the bottom, and many free electrons will be at the surface of P-type bottom layer, and then current will increase. So if you increase the voltage V1, you see that resistance of the bottom material is decreasing. So you can say that if I write here, say D, E, F, another point I am writing, if V1 increases channel resistance, you can say, or you can say concentration of electrons is increases, and hence resistance of channel, let me call it channel decreases, and current IAB increases. Is it understood? So with the application of or variation of voltage V1, you are able to control the current through a channel region. Channel means the region of electrons and the surface of the bottom plate. Is it understood or not? It is a voltage control current source, which is normally denoted by a symbol voltage controlled current source, denoted by this kind of symbol. Okay. This kind of symbol is used to denote it. So once you have the voltage controlled current source, small amount of voltage picked up by the microphone, that voltage will be controlling the current, output current, okay, current through AB can be controlled, and you can apply a voltage, higher voltage across AB, and that current may be good enough, and hence you can use this kind of device as an amplifier also, amplifier circuit. Understood?
Yes, sir.
So this is what a MOS capacitor, actually MOSFET is a full of capacitor. In the last class also I said. So further understanding was required. So MOSFET, so far you know, this is whatever I have drawn. I would like to delete it. Otherwise, I need a another. So let me do it here. So what I have drawn is a top layer. Then another layer here I have drawn, which is SiO2, which is a silicon dioxide insulator. And then I have shown a substrate E-type, okay, E-type substrate. So in this region we have many free electrons, which is called inversion layer. It is this region is inverted. Basically, it is P-type, lightly doped, and the concentration of electrons here depends on the positive charges deposited here by connecting a potential V1, right? This is our discussion. And I have shown that to flow current from one side to another, I did a connection here, this side, and connected a wire and then a supply voltage like this. You are applying a voltage here based on this V1 and this is V2. Okay, this can be also written like this or denoted like this. It is same. Do you understand this? It is indicated that point B is connected to ground or negative terminal of the battery. Point A is connected to positive terminal of the battery. Okay, same way. And this one is a bottom plate is grounded, means negative terminal of the battery is connected. Instead of drawing all the way from here to here, you can do that. Could you understand? These are the notations. Will be instead of connecting all the way up to here, you can denote it this way. Do you understand, Aman?
Yes, sir.
Now, I was showing connection in this way. Making a contact from the side. Okay. And then varying it. But in this way, side you cannot say is a cross-sectional view. Remember that whatever I am showing here is a cross-sectional view. Three-dimensional view may be in this way. You can draw it and show you. Okay, it is a cross-sectional view. Do you understand now? It is a kind of a break front on one side of the break I am showing. Is it clear? Yes.
Yes, sir. Yes, sir. Clear.
Okay. Cross-sectional view. So connection you want to give here. So it is not, and by the side of it, you will have another device. Okay, by the side of this device, another device will be there. By the side, this side, and left side, everywhere, front side, back side, everywhere you will have. So how can you make a connection like I have shown in the last slide? It is not possible. So connection is made from the top. Okay. Connection is made from the top. Connection is not made from the bottom. So what is done is to give a connection. Oh my goodness. To give a connection, what is done? From this side and top, in this way, this region is heavily doped. Once you heavily dope a region, the whole thing is your, this substrate or the p-type material is extended to left and the right side also further. Okay. It is not ending here, it is further, and this side is also there, and this side, because by the right side also have some fades, means not all around many fades are there, or this kind of device is there. So what you have done is from the top you have ion implanted and made this region heavily doped. If something is, as a semiconductor is heavily doped, what happens? Earlier it was p-type, means it was doped with boron. Yesterday you have said yes or no. Now you will be making a contact, N plus contact. What you will do? You will be ion implanting with phosphorus. Okay, and the p-type material has now converted into N plus type. A plus indicating huge doping. Too much heavily doping. Okay, and why it has been done? To make its conductivity very high. Is it understood, Pratham?
Yes,
Pratham is
sir.
there? Pratham, are you there?
Yes, sir. Yes, sir.
Okay. So by heavy ion implantation with p-type material, n-type material, pentavalent material, you have made it n plus region, and from top you give the connection. You call it this side instead of A, let me write D. This side instead of B, I am writing S. Okay. Source, because electrons are moving in this direction, source of electrons. Okay, and right side is D because it is draining. Okay, draining the electrons from supplied by source. So connection to be given from the top, not from the side. So I can write here as a point connection to OS or D to be given from top. From the side you cannot drill and put a wire because it is very thick and very large. So from the top it is given by unimplanting a point. You make point of contact on which you actually make a hole. Of course, this all region will be silicon dioxide, remember. Okay, silicon dioxide will be all over and will be making hole, and that hole will be filled with tungsten. Here, whatever you are seeing here, the contact for ash and drain is filled with tungsten. Okay, filled with tungsten to make a good contact with the N plus region. That is one thing. Secondly, one connection I have shown at the bottom here. In this point, you cannot give from the bottom. There's a brick is there, bottom. From the bottom, you cannot give the connection from. In this also, you have to give connection from the top. Okay. So possibly you'll be making p-type material it is. So you make another p plus p-type good contact you want to make. So with this p-type substrate, so p plus type you make, and good ohmic contact can be given here instead of giving from the bottom. See, the earlier I was showing here. Okay, the V1 connection, ground connection was here. No, it cannot be given. For demonstration, I was showing like this, and many books also shows like that. But it should be given to the top, from the top. Okay. This all body, this all are body or the substrate on which the MOSFET, N MOSFET is made, and that's what is shown here. Okay, so this is all about the MOSFET, and you take a substrate that is p-type, one which you make N plus region here, and you apply the silicon dioxide at the top, and on top of that you apply the polysilicon, and here you give the connection, and this portion you have given the connection. This is the connection for the gate voltage. This gate voltage is normally called VGS, gate to source voltage. Actually, source is grounded. Okay, this source is grounded. So with respect to source, gate voltage is applied. Why we call it gate? Because if you apply positive voltage at the gate material, that is the top material, then only electrons will be formed, available here. In this region, electrons will be available here only when you apply the gate voltage. Once you apply the gate voltage, then electrons, if you give the connection between the source and drain, then current will flow. Otherwise, gate is closed. Means if you apply 0 gate voltage, in this case, gate will be closed. If you apply high gate voltage, high in the sense maybe 1 volt or so, high low I am talking about. So high gate voltage, gate is opening for electron to flow or current to flow. Is it understood? Bushra, Akhtar? Is not there? And Harsh Tripathi, are you there? Harsh Tripathi, are you there? Harsh Tripathi, not there. Okay. Aman, understood?
Yes, sir, understood.
So gate is going to control the current flowing through the channel or from source to drain or drain to source. If you consider electrons, then from source to drain. You consider conversion current from drain to source. That's what the MOSFET. If you don't apply sufficient amount of gate voltage with respect to source, current will not flow. That sufficient amount of gate voltage which the amount of gate voltage with respect to source, because source is grounded, so negative terminal of the battery and positive terminal of the battery is connected to the gate, so gate to source voltage, which is called VGS. The amount of gate voltage with respect to source which causes an appreciable amount of current. Appreciable amount of current drain to source, so I'll write IDS, current amount of IDS, drain to source current, that gate voltage is called what? Tell. The amount of gate voltage with respect to source, that is the amount of VGS which causes an appreciable amount of IDS, that gate voltage is called what? Yes? Tell. The amount of gate voltage VGS which causes an appreciable amount of IDS is called what? Threshold voltage. It is denoted by VT. Okay. Another bit will be there. Normally I'll be using V capital T. That will be equals to 26 millivolt at room temperature, say 27 degrees centigrade. That is different things compared to this VT. This VT is, small t is threshold voltage. So until unless you are applying VGS greater than VT, no current will flow from drain to source. Could you understand, Aman?
Yes, sir.
Now, this is what I have shown by drawing, but convention, I mean, normally you'll see the diagram in the case of the various books in a different way, little different way. Basically, idea is same. Okay, let me delete all these things and try to. So what we understood is, if you want to get an IDS, you have to apply gate voltage. So yesterday also, as I was writing, IDS equals to 0 if For the condition,
VGS is 0.
if VGS less than VT, let me write, okay? If VGS is equals to VT, then we can get a good amount of current, which can be useful current, you can say. Second point is IDS equals to mu n C ox W by L into VGS minus VT into VDS minus VDS square divided by 2. Okay. This is for VGS greater than VT, but VDS less than VGS minus VT. Means VDS is very small. Drain to source voltage maybe 0.1 volt, 0.2 volt, 0.3 volt or so. It is not too much. So this current is in linear region, and we denote it by plot. This is your ID. Sometimes I write only ID. And this is your VDS. If VDS say 0.1 volt, 0.2 volt, 0.3 volt, 0.4 volt, in this way it is increasing. Suppose your VDS is small, the ID will linearly increase with the VDS. You increase the VDS, current is also linearly increasing. Okay, after that, if VDS is greater than VGS minus VT, then current becomes saturated, means it doesn't increase further, it becomes parallel, with the x-axis. Current ID is independent of VDS. This is linear, so it is called linear region, and this is saturation region. Okay, so for the current equation, IDS equals to mu n C ox W by L divided by 2 into VGS minus VT whole square. This is the case when VGS greater than VT and VDS greater than equals to VGS minus VT. Right? This condition is saturation region condition. This condition, remember, is for saturation, and this condition for linear, this condition for cutoff. Cutoff means no current. These are the equations. This derivation of this equation will be done in the next semester, 5th semester, if you are going to take the VLSI design as specialization, okay, or elective subject during that time. This all is not even there in your syllabus which we are discussing in this semester, but to make you understand certain things, it is required. So let me put a question here. The symbol of this MOSFET is like this. Here is the gate, this side is drain, this side is source. Okay, body is here. Body terminal is the one where you have the this is body on which on this whole thing, whole bottom layer, which is P type, is body. Okay, it is normally grounded. I have shown here from the bottom. Okay, but in the next slide I have shown that it should be connected from the top. Okay, so as can be shown here also, here you see same thing is shown in a three-dimensional view. This blue portion, whole blue portion is a kind of brick, and front view we are seeing from front side, and that is your body or substrate, p-type substrate, on which by ion implantation n plus green region is made. Okay, and then silicon dioxide gate silicon dioxide under the gate, which is red colored polysilicon, is shown here. The under the gate you have the brown portion, very thin, which is called gate oxide. I was showing earlier in this way. I was making zebra crossing type things. That is your gate oxide material. Okay, and the MOSFETs are isolated. The general question is asked that nowadays in a chip you have billions of transistors, then how they are isolated from each other, even though they are sitting on a semiconducting material. P-type material is your semiconducting material, on which all the MOSFETs, billions of MOSFETs are sitting. Okay, then how they are isolated from each other? Why not current is flowing from one node to another node, one terminal to another terminal? Okay, they are isolated by field oxide, very thick silicon dioxide. This is also silicon dioxide, SiO2, but very thick. Okay, hence it is thick. It is going to isolate this device from the another device around surrounding it. And you see that from top, this tungsten has been connection has been given up to n plus region. This side says source, this side is drain, and this one is gate. Is it understood how MOSFETs are looking in a three-dimensional view? Earlier I was showing only cross-sectional view. From here you can see the three-dimensional view. Yes, Aman, is it understood?
Yes, I understood.
Or if you have any doubt, anybody can ask. Don't keep your doubt. Of course, we'll be discussing this thing in the future courses, but to understand the course here, course says that CS and CD amplifier, and that too in high frequency. We don't know about MOSFET, and this has been put here. In future semester, we'll be learning in details, but since there is a module, rather not module, one topic in which we have to discuss the high frequency response of CS amplifier and CD amplifier, you should understand first MOSFET, how it is made, not only symbol. Yes, I am going to use this symbol here for the MOSFET, and you are also aware of the MOSFET symbol. Am I correct or not? Yes or no?
Yes, sir.
So normally, see, if it is a P MOSFET, it can be denoted as this, source and drain. Okay, it's the gate. This bubble indicates at the gate, a bubble indicates that the charge carrier is hole instead of electron. And if you don't have bubble at the bottom figure, it is an N-type N MOSFET or N-type MOSFET. This is N MOSFET, this is P MOSFET. Okay. Now, if I give some voltage, and its threshold voltage also. This MOSFET, say this is drain is 1 volt, source is 0.5 volt, and gate is say 1 volt, and body is grounded. Okay, and your threshold voltage Vt of N MOSFET, so I am writing Vtn equals 0.4 volt. Can you tell in which region MOSFET is operating? We have 3 regions, as I have pointed out, as cutoff region. The one is linear region. Linear region is also called triode region. Triode region, resistive region, linear region, unsaturated region, etc. Various name is there. Ohmic region is also called ohmic region. There are 4-5 names for linear region, but other one is saturation region. Okay, so 3 regions are there. 1, 2, 3. I have given the conditions also. Can you tell me this MOSFET and MOSFET is operating in which region? Though your amplifier, whatever you are going to discuss, will be always considered in saturation region, and why that can be discussed later on. But for your information, all the amplifiers, MOSFETs, and all the amplifiers are operated in saturation region because GM is higher. What is GM? You don't know. I don't expect also. But can you tell what is the
Sir,
yes?
it is working in a saturation region.
Saturation region condition is known. Let us check up. Saturation region says that VGS should be greater than VT. VGS should be greater than VT, and VDS should be greater than equals to VGS minus VT. That's what I have written here. He is telling that it is in saturation region. Let us check up. VGS is what? In this case, VGS means VG minus VS should be greater than VT. VT is 0.4 volt. I have written VG is 1 volt minus source is 0.5 volt. So it is greater than 0.4 volt. It is true? Yes or no? This is VGS is greater than VT. That is true, firstly. So it is on. It is not cut off. If it is less than, this is not true, then less than, then it was cut off. So once it is on, now we have to check whether this condition is satisfying or not. VDS is in our case what? Tell me, Aman.
0.5.
0.5 volt because 1 minus 0.5. This is 1. VD is 1. VS is 0.5. So it is 0.5 greater than equals to VGS minus VT. What is that? VGS minus VT. VGS we have got as 0.5 minus 0.4, which is 0.1. So it is true. It is true. So it is in saturation region. So I hope you can understand all these things. At this point, one thing I must say about P MOSFET. N MOSFET you have understood. Region operation you can understand from this discussion. But what about P MOSFET? Let me talk about the P MOSFET a bit. Then we'll switch up to other. I said that the condition, whatever I have written for linear region, saturation region, cutoff region is for N MOSFET. So what will be for P MOSFET? For P MOSFET, what will be the condition? If it is a P MOSFET, then what will be the condition? And we have not at all discussed about P MOSFET. In case of a structure, if I draw the structure of a P MOSFET, you take the substrate as N type, okay? N type substrate. N type substrate. In this, you can make P plus, right? By I am implanting it with boron in this way, okay? Boron you have implanted and it has become, okay, it has become P-type now. And there are several steps to do this thing. Then you have also similarly you have silicon dioxide layer. On top of that you have polysilicon and gate. It is polygate. Polygate. You have this drain and this source. Okay. Okay. So what happens in this case? In case of Epi Mosfet, if you apply a positive voltage, thing will not work out. Here a lot of majority carrier is here, electrons, right? N-type material you have taken for the substrate, and you have to apply a negative voltage at the gate, negative with respect to source. Negative with respect to source, you have to apply voltage. If negative voltage you are applying, so negative charges you are depositing here, correspondingly you will have, initially what will have, it will be repelling the electrons which are there as majority carrier in N-type material. Yes, Aman, are you getting?
Yes, sir.
So initially it will be repelling the electrons down because you have applied negative charge on the gate material. It is repelling down means what? Leaving behind positive ions. Are you getting my point? If electrons are repelled, it will leave behind positive ions. And if your negative voltage potential is further increased, so electrical field will be more. So those increased negative voltage or increased electrical field will attract the minority holes. Minority holes are there because of the thermal generation. Yes or no? Few
Yes,
here
sir.
and there, minority carrier will be there in N-type substrate. Those will be attracted by that strong electrical field at the gate, right? Now if you connect voltage between potential between gate and source and drain, you apply voltage source and drain, then the whole flow will start. In which direction the whole will flow?
Source to drain.
Source to drain, in this direction. Let me take a color. In this direction whole will flow, means conversion current direction and the whole flow direction is the same. Could you understand? So current will flow in this direction. ID is like this. So what is the requirement here to flow current in this drain to source to drain? Requirement is that you should have gate negative with respect to source. Source is this side. See that other side. So source of a P Mosfet by right. P Mosfet. Source is that terminal which is at, out of these two, source and drain, that terminal is source which is at higher potential. Here, out of this drain and source terminal, source is at higher potential. That is connected to VDD or positive terminal of the battery. Okay. And in case of N Mosfet, that terminal is source. So that terminal is drain, let me call drain, which is at higher potential. Higher potential. Means in case of drain in Mosfet, if I draw this symbol G ds. So this is drain because possibly this source will be grounded and this will be at higher potential. In case of P Mosfet, thing is different. Okay, source they are showing at the top. Doesn't matter whether it is top or bottom, but remember that source terminal is higher potential than the drain. Anyway, our point was that flow of current will happen in the P Mosfet only when there is a negative gate voltage with respect to source. Okay, negative gate voltage with respect to source, and if that negative voltage is good enough, negative enough with respect to source, then only that voltage is called the negative enough gate voltage for which the, let me write in this way, the negative enough gate voltage with respect to source which causes sufficient amount of current is called what? Tell. The negative enough gate voltage with respect to source which causes current to flow from drain to source is called what? In case of P Mosfet, Aman?
Threshold voltage.
Hmm?
Threshold voltage.
Threshold voltage. Vt P. We write P because it is P Mosfet, and remember that this should be what? Negative. So I was showing that plus 4 volt plus positive 4 volt, 0.4 volt was the threshold voltage of N MOSFET. Now it may be possibly minus 0.4 volt or so. Are you getting? Negative voltage is required at the gate, then only current flows from drain to source in a P MOSFET. Okay, so in this case, what you will write? Current equation we have written here. How will modify this, which will satisfy the? It should be written as VGS greater than VT. Okay. For P MOSFET, IDS equals to 0 if VGS greater than VT, and that region is called VT cutoff region. In case of linear region, we'll write VGS greater than less than VGS less than VT. Just change the things, greater than and less than. VDS greater than VGS minus VT. Remember that VT itself is a negative quantity. Here in case of this, you write VGS less than VT and VDS less than equals to VGS minus VT. Yes or no? What you did, just change the things, greater than to less than and all. Now I'll ask a question on this regarding the P MOSFET, and you have to say the MOSFET is in saturation region, cutoff region, or linear region, right? I have put the conditions here for your understanding. Now you will answer the question. Okay. Question is?
Sir, next class is started.
Okay, I'll take another 1 or 2 minutes only. Bear with me because I'll not come back to this. I want to know whether your understanding is complete or not. Just 1 or 2 minutes. So I'm putting the value here. It is 1 volt. It is 0.5 volt. This is 0.2 volt. And VTP is minus 0.4 volt. Tell me what is the region operation, then we'll switch off your class today. Could you understand? VTP is minus 0.4 volt. Source voltage VS is 1 volt, and VD is 0.5 volt, and VG is 0.2 volt. Tell quickly, it is working in which region of operation? You will be having exam today from 1 o'clock onwards. 10 question, 15 minutes. So be careful. Yes, tell Aman, are you getting this?
Sir, it's in saturation.
See, if on, for on, what is the condition? On condition is that VGS should be greater than VT. Then the P Mosfet will be on. So VGS is what? Tell me.
Yes.
VG is 1 minus 0.2. Yes.
0.8 volt.
0.8 should be greater than VTP, means minus 0.4. So it is true. Yes or no?
Yes, sir.
Yes is true. Okay. Now condition for saturation is that VDS should be less than equals to VGS minus VT. Here VDS is what? Tell. VDS is tell.
minus 0.5.
Minus 0.5
Minus
should be. VDS is minus 0.5 or not? Yes or no? Yes. Could you understand?
Excuse me, sir.
Yes.
So sorry to disturb you, but our next meeting has started, sir. Next class.
Okay. So okay, I am ending here. We'll start from here onwards in the next class. You can join that class, leave this class.